Hello. Welcome. Today we have another Leetcode question, another graph question. I know, guys, I love these graph problems. So let me read out the question. Right, this is maximum star sum of the graph, right? And you guys have an idea of what a star is, right? A star is basically, and the question defines about. Let me define it. A star is basically a node with a bunch of nodes connected to it. And the question even says, right, that a star graph is a subgraph of a given graph, right? It's a subgraph having a center node containing zero or more neighbors, right? So basically, a node on its own could also be, a star graph, right? If it has any number of neighbors, right, it could be a star graph. Like it is a star graph, I guess. I think Nico has a previous question where like they ask you to identify the star graph. So you're going to look for the one with like a certain number of edges, right, and a certain number of neighbors. I remember that question, but maybe not too fondly, or like not too clearly right now. But basically, now knowing what a star graph is, right, and it's loosely defined as even just a single node, right. What the question is asking us is saying the star sum is the sum of all the nodes present in the star graph. Okay, so basically, we are looking for a subset of the graph, right, that is going to return what the maximum star sum of that subset containing as most key edges, right? So basically, the question I've already read and I gave the guys a favor of not reading it again, but I'm just trying to explain that like every node could itself be a star sum, right? So we'll have to go through each single node, right? And basically the question is saying, right, like we want basically the star sum, right? That means the sum of at least sorry, at most what k number of edges, right, which is like the max for each node. Well, for example, look at this question, right? We have node zero, right? It has one. That's the node value, right? Like you have a values array, as the question also states, right? So node zero has a value of one, two has a value of one, and two. So one has a value of two, and so on and so forth, right? Now you see that the max sum is what 16, and why is it 16? You see for the node three, right? Node three is connected to its neighbor four, and it's also connected. It itself has like a value of 4, right, and this number 4 has a value of 10, right, which adds up to 14. And also this node itself is also connected to a node 1. So the question is saying, right, like the question is essentially asking, right, like for each of the nodes, right, which if it has at most key edges, right, like are you going to pick key edges? If you pick at most key edges, right, is it going to have the maximum sum? And if you are picking the edges, right, for three, you can also see that three is connected to six, is connected to five, right, and that's negative 10 and sorry, negative 20 and negative 10, right? So why didn't we pick this? Because the key we are given here is two, right? So if we are having at most two edges, right, then I choose, right, to pick what the maximum ones or the ones with like the highest values, basically, right? So basically, we are going to greedily pick, and we are going to go for each node because each node can be a star graph, right? As the question is saying, and basically with that star graph, I'll keep all the values of the neighboring nodes. Right? Like for node zero, for example, I'll keep the values of its neighboring nodes. Right. So the value of one is what two, which is the only neighboring node. And then I go through all the neighboring nodes of zero later on when I process them. And when I process that and I say, oh, maybe the max time I've gotten is two, and that k at most key edges, right? Like if that is what we get, right, and that is the maximum, then fine, we return that as the maximum when we go through the whole, all the nodes. But if that is not the case, right, then we go to the next node, the next node, and the next node, and you can see that here with node three, right, it has four connections, like connected to six, five, and node four and node one, right. But when we have our case equal to two, right, we are going to pick at most two edges. We are picking at most two edges. So we are picking the best of them. We are picking a 10. We are picking the one. Yeah, right, the one, right, which is the connection between what um sorry, not the connection, but like the value of 1, the value of 3, and the value of 10. So basically, how are we gonna keep our stuff? We're going to keep it in a priority queue, right? And when I keep the nodes later on, right? Like later on when I'm processing for each node, we keep them in a priority queue, right? We're gonna remove from the priority queue the least element and then add a greater element if so. The as long as our size is not equal to or greater than k, right? Maybe a lot more said, but the coding should be um I think a bit more easy for me to do. So we have an adjacency list, right? And then our adjacency list of integers, and that is going to be, and actually I don't have the size, so let me previously define that. Put int n, then it's going to take an instance of the vowels reference. Basically, the number of vowels we have dictates the length, right? So we have a adjacency list, but before we, do anything, right, we have to go through the base case. And one of the base cases is that what we have, for example, our k being equal to 0. That is a possible thing, and when that is the case, right, we have, and I've previously gone through the question, right, we have like weird edge cases, right? So when our k is equal to 0, right, then we have to pick the element with the maximum value. That is what we have to do. So that's our corner case, and I actually want to define that here. I'll say corner case, or basically edge case, right? That's what we call it, edge case. And our edge case is that if k is equal to 0. So before that, I want to define a variable, and I call the variable what result, and result is just basically we're going to take any element in the files array. But we're going to take the first element first, right, and then we go through the whole array to see who the max is, right? But we are only going to do that if our k hits our base case. This was k is equal to 0. So if k is equal to 0, then we loop through. Then we look through vowels and say for int I in our vowels, for example, right? I want the one with the maximum value, so that will be returned. So the result is equal to what's the maximum, right? Maximum of I, a maximum of whatever result is at that point. So at the end, we return results, right? This is the base case, corner case, and it'll come in handy later on. But if not, if our case is not 0, and we do have a graph, right, then we want to build our graph. And basically, as I was saying previously, that we want to build our graph with the edges, so with the values. Instead of using the node values, right? So then later on get the values in the value set. What I want to do is to just put in directly the values, right? So initially we want to keep we want to set from I to sorry I less than n and I plus plus, right? I want to put in an empty array list for every index, right? Like we normally do with the adjacency list, and then from there I add the corresponding edge, right? So I'll say for edge, sorry, for edge in edges, right? Come on. For edge in edges, right? Int u is the first element, kind of source node, and this is bi-directional, guys. So edge one, right? And now I want to add instead what's the value. So I'll say for ADJ of u, right? So for node u, I want to add the values of v. Right, so I initially add v, right? Whoever is a neighbor, and for v, I add what's the values of u, right? Yeah. So that is done here. Cool. Right. So we have this. We have this. Now you want to process each node because as I previously explained, right, like each node could be a star graph based on our definition here. So if it is, right, then you want to process for each node. So I'll say for int I is equal to 0, right? Then I is less than n and I plus plus, right? And then if our result hasn't changed here, right, then we want our result to be equal to what? Result, sorry, max, right, which is the max value of what not just result, whatever its value is. Then back to the top key, right? We want the top key values of every node, and then we add that. So you see, for example, here, right, the top key was what um, not just the node itself, right? Because the node itself will be added, but what the corresponding neighbors, right? Like for neighbor 1 and 4, for example, right? 2 and 10, right? That adds up to 12 plus this becomes 16, right? So top k, I want to call a function, right? Top k, and then I feed that function the adjacency list. I also feed it the current node that we are on, right? Which is I, and then I'll feed it the corresponding value of that I node, right? Because that was what we started with. Like we are dealing with node 3, right? The initially our result will be what 4, and then we do the additions and stuff from then on. And then not just that, I also want the key value, so we keep that and use that to you know keep our priority queue as it goes on. But if everything is done, then we want to return our result, right? And then basically what is public and it's going to return an int, right? So it's going to be top key. It's going to take the adjacency list, so it's a list of friends, adjacency list. We need a node value, and then we need our result, and then also what we need the key. So now what do? We first create a priority queue, right? Because the priority queue is what we're going to use to do our work basically. And our priority queue, I want to use taking integers. Sorry, it's gonna call PQ. Priority queue. So just a simple priority queue, right? And basically, this is going to sort it in ascending order. So now I want to go through um, the array list, right? The array list that corresponds to our node, current node. So I want to call that list, and that is what is going to be adjacency list of its node, right? Now, so for int k, no, for int I in list, right? Then we're going to ask ourselves, can we add it to our priority queue? Yes or no, right? And that is going to be like if the priority queue size, we want the priority queue to have at most the size of k, right? So if the size of the priority queue is less than k, right, then we are free to add. We do not have to worry. We do not have to worry about like you know replacing replacing values and stuff like that. So we just have to add, right? Till is equal to k, so we say priority q dot add what you add I, right? If not, right, then else if, right, if our I, we want to check if our I is worthy to be in our priority queue in the first place, right? So if our I is actually greater than the first element in the priority queue, right? The first element in the priority queue, when it's smaller than our I, then it can't be the greatest element, right? The I will be greater than it. So we want to take that off. And actually, I want to use priority q.peak just to check instead of like actually remove, right? So if this case is fulfilled, right, now I'll say priority q.pull, which will remove the smallest element, right, first, and then priority q.add I, right? So then we add I. So we make sure that in our priority queue at all times we are having the maximum values, right? Cool. Now, if that is done, right, then what do we do from there? Then we add every element in our priority queue. Now everything has been processed to our result, right? So it will result actually. So basically, while our priority queue is not empty, right? While it's not empty, then I'll say our result plus equal to our priority queue dot pull. Basically, remove every single element remaining in our priority queue and add it to result, and then after that we add what return results. Basically, so that should be it, guys. Let's just run this. Oh no, a bit longer code than so we have a compilation error actually. Hold on. Um. Oh, integer. Is it okay? Cool. Fix this. The signatures, right? So we passed the first two cases, right? And this is why this second case is when we have case equal to 0 and we had an empty set, right? Like we were supposed to return the highest value in vowels. That's why I have our corner case here. And you see, we are passing the first two test cases. Let's see, how we do overall. Oh, so we filled something cool. So I just want to keep this and go through and look for our possible bugs, guys. So one other difference between like what we what previously did and this is that for these cases, right, we are adding because of the way that the test cases are structured, right. Um, if it is, if its values, right, if we have like negative values, we do not want to add them to our adjacency list. And why is that the case? Because we are actually looking for the maximum. So negative values are not going to help us at all. So in fact, what happens in the end is that we have to make a check here while we are building our graph, and we check that if what vowels or v is greater than zero, right? If it is, because of, and also because of the way that test cases have been done, if it is, right, then we check, then we add, and it's free to add to our adjacency list, and the same goes for what, sorry, the same goes for vowels u, right? If that vowels u is greater than zero, then we want to what, basically have this addition to our sorry, not to our priority queue, but to our adjacency list, right? So I have that done, right? And this case should pass now. Um, the third case here, right? So basically, that's it. Why we are not going to use the negative numbers. That's why we do not have them. And actually, they do mess up your stuff down the line. But if your case equal to zero, right, because of the way the question is structured, if your case equal to zero, then what you have to do is to basically return the max value in val. And if it happens to be -5, for example, as in this case, because there's only one possible star graph, then you return that. So everything overall, right? What's the runtime? Well, basically, we do have an n log n, right, element here, right, in our priority queue, and then we do that n time. So basically, at the worst case, we have an element with what, n neighbors, right, and then it's basically the n. Right. We are thinking of it in terms of the worst case, right? So it's going to be n squared log n, and that'll be the runtime of the whole algorithm. I hope you guys enjoyed this video, or was helpful in some way. If so, please subscribe, give me a like, and I'll see you guys on the next one. Peace.